So we find the equation for the superconducting gap within this BCS theory, and we actually went into the also into the value of the Yang equation. We also got this equation for the density of states in the BCS theory, and I show you some experiments in which actually one can see this density of a state, because density of a state in systems in which you have in which there is no Andre reflection, so practically the differential conductance actually map this density of states. We have this, and I show you this. So this is the density of a state here, which is essentially between 0, when you increase the voltage and go from energies from 0 to delta 0. Okay, let me do this. What happened? Oh, okay, so when you go in, so there are no states, so you should get 0 conductance, and then there is a jump. You have a maximum somewhere here for density of a state. You will get large conductance, and eventually, if you still increase the voltage, you will get the normal conductance. Right? And so this is what essentially you see here. So this is differential conductance. In that case, was aluminum surface, so you have a tip, and you just measure the conductance between this tip and the aluminum surface. Okay. So this is a scanning tunneling microscope. So you have a vacuum barrier between the tip and the surface. That's why this reflection or the transmission that you have is dominating. I will explain a little bit, but the thing that is dominating is the specular reflection. So there is no Andre reflection in this experiment. So that's why you have this 0 here. And then, well, you see, and that is actually mapped this. So 0 here, you get the maximum, and then you go to the normal conductance, which is 1, it's just a quantum of conductance. So from this experiment, so what you can do is just to estimate the gap. So it is a very common experimental technique to estimate the gap in your material. So to measure how much is the gap. Because if you know this energy here, or the energy corresponding to this bias, then you essentially what you are measuring is the superconducting gap. So we also, derive this Bogoliubov-Yang equation, which is very useful for, treating problems in which you have inhomogeneities and so on, because it allows you to do the calculations in real space. So we have also some schematics of this band structure for the BDE equation in a homogeneous system. And then we also consider a spin, so we generalize this initial BDE equation that we have without a spin, how it should look like when you have a spin. So I must say that you may find this equation of the Hamiltonian BDE written in different ways in different books. It just depends on the order of your bases. So if you change the order of your bases, it's going to change a little bit also this Hamiltonian. Okay. So this, in this case, is just written in a basis in which the two components are just the electron-like or the particle-like components, and the whole components are written like the time reversal of the particle components. That's also, you have this term here with this T, which is the time reversal operator in this whole line block. All right, so not sure. Okay, it just takes some time. So we also have an introduction, brief introduction to Josephson junction. So what are these Josephson junctions and why they were useful for? So we saw that you can do squids and then use this squid for magnetometry. So they are very sensible. You can measure with them very small magnetic flux. So we also have a little bit short discussion about how to also use this Josephson junction to build superconducting qubits. So how we can, so if we can quantize this LC circuit, we will get something like a harmonic oscillator. So we can get a spectrum that is similar to the harmonic oscillator, which is still not good for doing qubits because all the levels are equally spaced. So you cannot distinguish between transitions between these states. So the way to get rid of this dependence was to introduce some harmonicity, and this we can do it with the Josephson junction, right? So that was the idea. So when you include the Josephson junction, then you start to get states which are not equally spaced anymore. So you can distinguish between the ground, transitions between the ground and fair excited state from other excitations. So then you can use the ground state, let's say, as the zero of your system and the first excited state as the one. So you can build the qubit with this. So there were also some issues with the charge. So there could be some fluctuations in the charge. So sometimes we'll have to do actually some tricks and get into a, essentially your levels may oscillate with the charge. So for this, you need to do something. You need to go to a regime in which the energy of the junction is much larger than the energy of a capacitor that you put actually to regulate this charge. And so this is the so-called Transmon regime. And so you see, for instance, so this essentially are the levels of your junction as you change the gate or the charge. So you have fluctuations in the charge. So the energy spacing between this ground state and the first excited state is going to change, and that's not good because it's like your qubit, the difference in energy is fluctuating, so you don't know exactly what is the energy, the transition. So you need to go into this regime in which then they become flat. So they are completely, they don't depend anymore on this charge fluctuation. So this is the regime that is called the Transmon regime, and you can build qubits in there which are called Transmon qubits. These are the superconducting qubits that are nowadays used in IBM quantum computers that you can access actually through the cloud to these quantum computers. Okay, so we also have an interesting thing that was related to the scattering processes that you have at the interfaces between normal and superconducting materials. And we can have a couple of different reflections. So one is just the usual reflection we have, a specular reflection. So electron is coming and then it's reflected. And we have also another reflection, which essentially an electron is coming. It cannot enter into the superconducting like an electron because if the energy of, if the Fermi energy is inside the gap, there are no single particle state for this electron to be there. So the only way this electron can enter in the superconductor is to enter and form a Cooper pair. So by forming a Cooper pair, then a hole is reflected. So in this process, you have an electron is coming, form a Cooper pair, an electron, and a hole is reflected back. So I think we have also this picture here. So if you look at it, you can change the interpretation of this phenomenon independent of what are you looking at. If you look at everything in the particle interpretation, not this particle hole interpretation, essentially what you are seeing is just, you have these two electrons, one with energy a little bit above the Fermi energy, so that's why when you put the bias, so that's why you are shifting the energies, and then another with an energy a little bit below the Fermi energy. So the total energy is zero, so one half plus Fermi energy plus something, the other Fermi energy minus something. The Fermi energy is the zero of the energy here. So, and then these two electrons enters like a Cooper pair, but you see when this electron that I have here, I needed to form the Cooper pair, so it leaves a hole below the Fermi energy. So that's why in the particle hole picture is what happens is an electron is entering and a hole is reflected. All right, so whether we can see this or not, it depends on the kind of interface you have, okay? So you have, let's say, if you are in this situation that you have, a normal material, let's say a metal, but then if you have a barrier between this normal metal and the superconductor, that will be for the case of this, this experiment I showed of the surface of aluminum with a STM. So you have a vacuum barrier between the tip and the surface. So that, and then these, the things are going to be actually dominated by just reflection because you have a barrier. Okay, so this barrier will just reflect the electrons. So essentially, if you have, if your Fermi energy is inside the gap, electrons are not going through because there are no state there. You can have, essentially, you don't have Andreev reflection either because the barrier is reflecting your electron back. So you will get zero conductance, okay? Now, as you start to increase the Fermi energy and it goes above the superconducting gap, then you start to have single particle excitations free for this electron to go, so they can then just tunnel normally. So eventually you will go from zero at, if your Fermi energy is inside the gap, to a finite value if your Fermi energy is above the gap. Okay? So when the Fermi energy is equal to the gap, then you will have a maximum because we know that this condition will give you the maximum density of states. And as you increase further the Fermi energy, well, you just go to the, essentially, it just, if your Fermi energy is high here in this region, so it's just like a normal material, so that you don't see superconductivity anymore for this transport. So what you will see is just the normal conductance. And again, so this is what was observed in this experiment. So you can actually see here this behavior. So again, so for energy below the gap, you have zero conductance. At energy equal the gap, you have the maximum of conductance because, well, you have also the maximum density of a state at this value. And then as you increase further the bias, you will go to the normal conductance, okay? Now, if I don't have a barrier, then actually these electrons can undergo Andreev reflection. And again, so that's what happens. So if my Fermi energy is below or inside the gap, then I can pair, I can have this electron coming from a Cooper pair and be reflected as a whole. Now, what is entering in the superconductor is a Cooper pair, which have the charge is 2e, is not e. So I will see, instead of the normal state conductance, I will see twice, because the Cooper pair have 2 electrons, twice the normal state conductance. Okay, so for this, if the spectrum is Andreev reflection dominated, because you don't have a barrier, you will see at zero, for bias between 0 and the gap, you will see twice the normal conductance. And then as you increase the energy and you go above the gap, then Andreev reflection starts to be suppressed and you start to get, again, specular reflection. So you will go back again to the normal conductance. And this is more or less what is seen here. So here you have an niobium tip, which is in contact with copper. And you see here, let's say at 0 or, for energies inside the gap, you see this twice, so the conductance is here. So I have 2 is 2 times the normal conductance. And so I'm trying to increase the voltage, so it just goes down, and it is very large the voltage, you just get again to the normal conductance. Now, why it is important? Well, it is important because actually this reflection, Andreev reflection, also depends on the spin polarization, right? Because let's say if I have much more spin up than spin down, I not all my electrons with a spin up will succeed to do André reflection, because they have to be reflected like a hole with a positive spin, but if there are not enough channel for the positive spin, they cannot do that. So essentially, one can use this André reflection to measure the spin polarization of materials. So here is, it's a couple of examples. So this is the example that I showed you before, which is, for this niobium copper. So there is no copper is non magnetic in that case, niobium either. So there is no magnetism, there is no spin polarization. You get what we get. But now you put a material that is spin polarized. For this case, I went here to a very extreme case of this chromium dioxide, which is nearly a half metal. So it's almost 100% polarized. So you go to the Fermi energy, so you have only carriers, let's say, with a spin up, okay? Now, assume this spin up wants to enter and want to form a Cooper pair. So this spin up will have to form a Cooper pair with spin down. So it has to get reflected like a hole with a spin down. But you see, there is no state here for this hole with spin down to be reflected. So then the André reflection is suppressed. And as the André reflection is suppressed, then your conductance go from 2 to 0, okay? So if you start with conductance from 2 and you start to increase the spin polarization, this conductance will go down, down, and when you have 100% spin polarization, André reflection is completely destroyed, and you get to 0. So if you look at how much this conductance is different from 2, you can figure out how much is the spin polarization that you have in your system. So here are these experimental curves for different situations, different materials. So nickel iron is also, you have a spin polarization, but it's not that strong. From chromium dioxide, as I mentioned, it's just half metal. So it's almost 100% polarized. And so you can actually find some simple equation that actually link the current spin polarization to this conductance at 0 bias, which is, just from this expression, you just measure your conductance at 0 bias, and this will give you the current spin polarization. All right, so that's what we have in the, I'm finishing the last lecture, and then today we will start a new journey, which will be the journey through topology and how we can classify topological phases of matter. So we close here for a moment, and then open my other file. And this is the plan that we will start today, and we'll continue tomorrow, because most probably we won't have time to go through all of it. So the plan is to go to some concept of topology and topological invariants. Then we will see what are the consequences of this topology, essentially through the Ball boundary correspondence. We will see how to classify topological states, and so how these topological states actually are linked to the magnet structure of the systems. And eventually, so we also will go through a simple model. So this is probably the simplest model one can have for topological states, called the Suchriffe-Higge model, or SSH, and it's very nice because you can see the results just from the model, actually. Still, there are some things that you need to do numerically, but most of the things you can actually get it from the model in a very clear way. So I'm not, I'm going to repeat a little bit something that I have in the colloquium. Not sure if all of you were in the colloquium. So, well, first, topology is a branch of mathematics concerned with the spatial properties preserved under continuous deformation. So it is a characterization of geometric objects on the basis of continuous transformations rather than on their specific shapes or form. And I have here, for example, this picture in which you can start with the donut and deform it continuously and go into a mag. So these two objects for a topology will be the same thing. So they are topological equivalent. So you don't look exactly at the exact form, but how one can go from one into the other through a continuous way. So there is a Fermi's theorem, which is called the Gauss-Bonnet theorem, and it says, essentially mathematically is this expression here. So you have the integral over the curvature on a closed manifold, on a closed surface. So it is warranted that it's going to be equal to 2 pi this Euler characteristic. So the function here chi, which is an integer number. So it's 2 minus 2, and g is also an integer number. It's a genus. So this is an integer number. And as I mentioned in the colloquium, it's actually an amazing property in the sense that you can have this surface, you can deform the surface, so in a way that this k here is going to be very different because you are deforming it. Still, you will get the same number here if you don't make a hole to this surface, okay? After the integration. So the genus in that case is, essentially is telling you how many holes this manifold has. So let's say you have, for this sphere, you have g equals 0. If you have a donut, so you have a hole, so g equals 1. And you have a pretzel, you have g equals 2, and so on. So this helps to topologically classify these objects. And one cannot go from one, so you see, one cannot change g continuously because it takes only integer values. So I cannot go smoothly or continuously from g equals 0 to g equals 1. It has to jump because it's an integer. So it means also I cannot go continuously from donut to the sphere, or from sphere to the donut. I will have to make a hole, which is not a continuous transformation. Okay, so this also explains why the object that we have this structure, we have certain stability, because let's say it cannot go. Let's say that you have the donut, it cannot go into the sphere continuously, it cannot go to a pretzel continuously, so it will have some stability. It will remain there for some time. And this, I show this video which more or less show this. So you see when you do these small rings, they stay there for quite a long time. So in comparison to other things, that have no structure, when the ring is there, so you see they stay, they have certain stabilities. And this is just it's topology, because they cannot, go continuously into other things, so they stay there for a longer time. So the idea was actually, was explored by Lord Kelvin many years ago, trying to explain the stability of atoms. We now know stability of atoms from quantum mechanics, but before quantum mechanics, it was not clear why atoms were stable. And so one of these proposals from Lord Kelvin was that the atoms were essentially the ether, forming some of these topological structures. So actually he had a complete periodic table with all these nodes for different elements and so on. It happened that, well, there is no ether. So after this experiment of Michelson and Morley that demonstrated there is no ether, all this just was forgotten. But it's something interesting from the past. So it's probably the first time that topology enters in physics. So for us, where is this topology? Well, the topology may be, most of the time for this course essentially will be in K-space. And you can see how this may appear easily. Let's say that you have this two-dimensional system. So just measure that is two-dimensional, and assume that we have periodic boundary conditions in two directions. So if I have periodic boundary conditions, then I will be matching this edge with this edge. So if I match, I will have a tube. And then if I match this edge with this edge, I will end up with this torus. Okay. So you see how this topology is building just from there. Most of the time, that's what we have. And for this course, that's what we have, topology in K-space. But it depends what you are investigating, right? So if you are investigating skyrmions, magnetic skyrmions, then it could actually, the topology may be actually refer to the real space. Okay, so these topological phases of matter were, I'm not say introduced, but more popularized by these three guys here, Taules, Halley, and Kosterlitz. And they got the Nobel Prize in 2016 for theory of topological phase transitions. And the idea is this, that you start with some, you start with some topological object and you start, you can deform it, but at some point you make a really strong perturbation, so a non-continuous transformation, and just can jump into another topological class, like here. So you can, let's say, start with, with the spheres, then at some point you open a hole, you get into a mag, you deform it into a donut, and at some point you open another hole, so you get to another. So you may have transitions, topological transitions, within these objects that have different topological number, okay, or genus in that case. But this can be also extended to the case of topology in K space. Now, the interesting thing is that when you have these topological transitions, some things may emerge, some new things may emerge. And these new things are typically some states that are at the border between topologically trivial and topological regions. So here are a few examples of this. So you can have the so-called quantum Hall effect and the quantum Hall effect. So you have these edge states. They are running, through the edges of the system. You can have topological insulators, so two-dimensional topological insulator. You have this pair. So here you have only one. Here you have pairs of edge states which counterpropagate and have positive spins. Or you could have topological superconductor in which you have these Majorana states at the ends of this. It's a little bit like a wire here. So you have the emergence of this state, and this is actually guaranteed by the so-called Ball boundary correspondence. So the Ball boundary correspondence is just a theorem that will tell you that there will be localized states when you have a boundary between a region which is topological trivial and one that is non-trivial, okay? So this new here that I'm putting here, these are the topological invariants for these phases. I will, talk a little bit more about this later on, but that's the idea. So you have a system that have some topological invariant or belong to some topological class, and then this system have a border with another region which is topological trivial, then it is guaranteed that you will have some bound states at this interface, okay? So what is the interesting thing here is that actually you just can have, you just have a look at the Ball properties of the system, and it tells you what will happen if you have a border, okay? So let's say that I have this finite system. Let's say, okay, it's finite, so it's here. What I can do is, okay, I just can solve my problem as if this was not finite. If I have periodic boundary conditions, go to infinity. I can calculate my invariance in that case. It's easier. It's much easier to calculate systems with periodic boundary conditions than systems that are finite. So I can calculate my topological invariance, and I have included anything about boundaries in my calculation. However, this topological or this Ball boundary correspondence theorem will tell me, okay, that's what you have, independence of what is your topological number. If you put border in your system, you will have these states or not. So I can know whether I will have these boundary states or not just from calculation from the bulk, okay? That is the important thing here. So this illustrate a little bit how these states can occur. So these boundary states, let me show you this example. So this is an example of, let's say that you have a semiconductor So we have this band structure in the first classes we have here, the first lectures. So, and typically we have the conduction band, so we have S states in the conduction band, and then we have valence band with P states. For simple semiconductor, we have actually like 6 P bands, 6 valence bands. I just put one for this, illustration. And let's say that we have, this is actually the normal band structure of the material. But you can engineer this band structure, and if you engineer the structure, it can happen that you may have an inversion of this band. And by inversion, it means that you may have a material, so in which the bands are inverted. So the S type now is here, and the P type is here. So you have this, suppose you have these two materials. So you have a material with this normal bulk band structure, and you have this with band invert structure. Now you see at the interface, so these two materials, they have a gap, right? So there is a gap energy here. There is also an energy gap here. But at the interface, you know that the gap has to be closed, and you have to have an state with an energy that is inside the gap. And the reason is very simple. How, let's say that you have in this, you have an electron in this P band, okay? So when you go through the interface into the other, so this state cannot go, the energy of this state cannot go through this S because they have different symmetry. So it will have to go from P to P and from S to S. So it has to cross, at some point, it has to cross the gap. So it will have to have an energy that is inside the gap. So you have to close the gap when you go through the interface. So away from the interface here, you have a gap. When you go through the interface, you close the gap, and outside, to the other side, in the bulk, you also have a gap. So then you will have these boundary states close to the interface with an energy that is inside the gap. All right? So this could happen in the so-called two-dimensional topological insulator. Then you have H states, or you have in three-dimensional topological insulator, you will have surface states. So another system which you can see this, and probably is actually the first, I would say the first experimental proof of these topological properties coming from the so-called quantum Hall effect, which is a generalization of this classical Hall effect to the quantum regime. So just to remind you a little bit about the classical Hall effect. So in the classical Hall effect, so you have just a layer, so let's say a metallic layer, you pass a current, so the current is in this direction, so electrons have negative charge, so they are actually running in this direction. And if you put a magnetic field which is perpendicular to the layer, then you will have a Lorentz force. The Lorentz force is essentially given by this cross product of the velocity, which depends on the direction of the electrons are moving, so the direction of the current in that case, and the magnetic field. So this Lorentz force, so if the electrons are moving in this direction, will act in this perpendicular direction. So it will push the electrons to go to one side, okay? As you keep the current going, more electrons and more electrons go through this side, but the electrons cannot go forever to this side because when charge starts to build, well, you have a lot of charge here now. The next electron, you have the Lorentz force, but you have the repulsive force of the electrons because you have accumulation of charge here now. So at some point, you get into a steady state, okay? So, and then you get some accumulation of electrons here in comparison with the other body. So essentially what you get is a cross voltage, okay? You get an electric field in the perpendicular direction to the current. This is the Hall effect. Now, if you increase this magnetic field and you go to the quantum regime, so this, what you will get is something that this ratio between the current and the transverse voltage, which is called the Hall voltage, becomes quantized, okay? So this is actually the real sample they use in the experiment. And from this experiment, this guy here called Klaus von Klitzing got the Nobel Prize in 1985. The effect is called the integer quantum Hall effect because it's quantized. So this conductancy, or the Hall conductance, which is the ratio between the current in one direction and the perpendicular or Hall bias, is quantized in units of E squared over H, which are constants. So E squared, E is the charge of the electron, is a constant, H is the Planck constant. So, and this quantization that you get is actually amazingly accurate. So it's 1 in a billion. It's probably the more accurate measurement you can do in a solid state system. Okay? So why it is, and you see, even at the macroscopic level, I can see that these samples are far from being perfect. Okay? So, and by the way, so you go microscopically, you will have disorder because you have impurities and so on, and still, this effect is astonishingly accurate. So this quantization, even if you may have more or a little bit more or less disorder, which in a normal situation, it just will change a lot your results here, still quantize very, very close to this 0, 1, 2 times or 3, this quantum of conductance. And the reason for that is actually topology. So if we look at the, how the electrons are moving in this integer quantum Hall system, so what happens is more or less what I have in this picture here. So this magnetic field is very large, so we have cyclotron orbits, so the electrons start to make this cyclotron orbit that we see here. So inside the bulk, the material becomes insulator because, well, the electrons cannot propagate, let's say, from left to right to carry a current because all of them are just in these circular orbits. Now, you go to the edges, however, so the electron cannot complete this circular orbit because, well, it cannot go out from the sample. So then you have this so-called skipping orbit. So it just go here and then it cannot continue the orbit, so it just reflected back and then, so it's doing this skipping orbit. And it's going in this direction in this edge and in this direction, in the opposite direction in the other edge. Okay? So when you apply a bias, what you do is you favor the population of one of this level. Let's say you favor the population of this level, and then you get the current. Right? Now this current is going to be dissipationless. Why? So when you have dissipation in a circuit, it just comes from backscattering. So electrons, let's say, come, hit an impurity, and go back. It cannot continue. So this give you resistance, and we know this also from resistance you can have Joule heating, so there is dissipation in there. But what is the point here? So the point is that this electron cannot go back because there is no other channel here. So to go back, it will have to go to this other channel that is, coming through the, in the opposite situation. But if your sample is wide enough, so it could be several microns from this edge to the other edge. It's very unlikely that these electrons will go through all this to get back, right? So essentially, the electrons will be just going there, and if you put impurity, actually it just will go around impurity and will continue instead of going back because there is no channel for going back. So this will give you this dissipationless current in this, and this is one of the big attraction of these topological materials. In that case, it's not so convenient because still you need to keep this magnetic field very large so that you have this. But there are other materials like topological insulators in which you can have these states without the need of an external magnetic field. Now, you look at the energy of the states. So let's say this is an edge, this edge at x equals 0, and this is the edge at x equal W. Okay? And you look at the energies inside this system, what you get is these blue lines here. Okay? So in the bulk, you get this dispersion is flat. These are the Landau levels. So the dispersion is flat, the velocity is 0. So it just tells me, they are the electrons are in this cyclotron orbit, but they are not moving, okay? So the group velocity is 0, then they don't contribute to the current. So it's an insulator in the bulk, okay? If you go to the edges, well, you have velocity. You see the velocity is just the slope of this energy dependence. So here the slope is positive, so you have current direction. Here is negative. On the other edge, you have a negative, an opposite direction. Now you start to deform this, because this calculation here, the blue lines, is for a clean system. There is no dispersion, there is nothing. But let's say that you start to deform the system and put impurity wherever you want, and you start to deform. So this, may not be like this anymore. It may be like the black stuff. This won't change the current because the current is just given by the number of channels that you have at these edges, right? And it doesn't matter how I deform this blue line as long as I do it continuously, so I don't break it or I don't open a gap, I still will have this, this crossing of Fermi energy with the channel, okay? So if I have the blue line or I have this black line, I will still have one edge state. So I will still have the same conductance, okay? If I have two edge states, I will have twice the number of conductance. So this quantization that we have is essentially how many edge states you have, okay? And this I cannot change it by this smooth transformation of the energy dispersion. I can change it, of course, if I open a gap, right? If I break this, yeah, then I will. But this is not a continuous transformation. It's not easy to make a gap in this system just by putting impurity, okay? So this is essentially the idea of this topological protection for this system. So essentially, this phase here in which there is no gap corresponds to topological state with a given topological invariant. And this one, when I open the gap, corresponds to another state with a different topological invariant. These topological invariants are integer. So it's like going, let's say, from donut into a sphere. And I know that I cannot go easily because this number have to change. And this is an integer. It cannot go continuously from one value to the other. All right, so this is the idea for the topological protection. And so essentially, it's, in the bulk, it is more or less the same illustration that we have before. In the bulk, we have this gap, so it's like essentially an insulator. But when you have the edges, this edge, cross the gap. So here I have only one, so I put this infinite here. But of course, if I take into account another edge, then I will have the other one, and then it will look like here, okay? All right, so, and again, so the important thing is that this backscattering is then suppressed because there is no way for this. It's like if you are in the highway and you go, so you cannot go back the same highway back, so you will have to go to the infinity and to get back to, to change your direction, okay? So, and then, this actually is the huge motivation to use this kind of materials in electronics because it will decrease the dissipation. So you can then forget about the need for cooling the system and so on. Okay. Which is actually one of the big problems nowadays, is just heating in these electronic or non-electronic materials. So this is an example of this, some topological states, but in general, we may have many topological states, many topological classes, so there is a way to classify these states. And so I will consider this way of classifying is not the only way that you can have for classifying topological materials, but it's probably the most used one. And it's called the Atlan-Zimbauer classification or AC classification. And this classification of the topological classes is based on fundamental operators of fundamental symmetry properties, namely time reversal symmetry, particle hole symmetry, and chiral symmetry. This chiral symmetry is sometimes also called sublattice symmetry. So in the same way we were, classifying these other objects according to the genus, 0, 1, 2, 3, well, now we have some numbers for these different classes. So there are 10 classes in this AC classification. If you add other symmetry properties, you may have actually more classes. You can extend this, okay? Now, what are the important symmetries that I will have here? So, time reversal symmetry. What that it means? It means the Hamiltonian of the system commutes with the time reversal operator, this tau, okay? Particle hole symmetry. It means that the Hamiltonian anti-commute with the charge conjugation operator, this C. So here this square bracket is commutator, here the curly bracket is anti-commutator. Okay? And for the chiral symmetry is also if the Hamiltonian anti-commute with the chiral operator S, then it have this chiral symmetry. Now these operators T, C, and S may square, the T may square to plus minus 1, C may square to plus or minus 1, and S is equal, S squared should be here actually. There is a misprint there. Okay. So let me explain a little bit how to read this table with all these things in there. Okay, so what we have here in this column the classes. So these classes are called A, A1, A2, A3, BD1, C2, D, C, D3, and C1. And here we have, time reversal symmetry, particle hole symmetry, sublattice symmetry, or chiral symmetry. Here there are some dimensions, D1, D2, D3. This dimension is the dimension along which you will have translational invariance, okay? If I have a wire that has translational invariance in one direction, well, this is D is equal 1, okay? All right, so what the zero means here in this table? So the zero means that there is no such a symmetry. For example, this class A means that the system doesn't have time reversal symmetry, it doesn't have particle hole symmetry, and it doesn't have chiral symmetry either, okay? So what is the C and C2? These are the kind of topological invariants that describe your system. Z essentially is like the set of integer numbers, right? So the topological invariant is going to be an integer. Minus whatever, blah, 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 0 plus whatever, so integer. And Z2 is C model 2, so it's essentially 0 or 1, right? Okay, that is essentially what it is. And so independence on the dimension and the class, the system may be, be characterized by one of these kind of topological invariants, okay? Z or C2 in these cases here. Now, what plus, 0 again means this symmetry is not there. What plus and minus means? It means the symmetry is there, and then the operator square either to plus or to minus, okay? So let's say you are in class A1, it means, so if I read here, I see, okay, there is no chiral symmetry or sublattice symmetry, there is no particle hole symmetry, there is time reversal symmetry because it's not 0, and the time reversal operator is squared to plus 1. Okay, that is the meaning. If I go to class BD1, so I can see all the symmetries are there because none of them is 0. Then the time reversal operator is squared to 1. The particle hole operator, the charge conjugation operator is squared to 1, and the chiral operator is squared to 1. Okay. So what will be the topological invariant? So it will be a C topological invariant for D equal 1. All right, so that is essentially how to read this table. Now, one of the things that are important is how to define these topological or these operators, right? So it can be actually quite tricky sometimes. So what is the time reversal symmetry describe. So again, so we will have time reversal symmetry if the Hamiltonian commute with this time reversal operator. And time reversal operator, what that is just change t by minus t. It leave x unchanged. It will change p to minus p because p is essentially like the velocity, so it can change t by minus t. I will get moving in the opposite direction. So, and from this, that t, leave x unchanged and change the sign of p, you can deduce this equation here telling you that it must be proportional to the operation of charge conjugation, of complex conjugation. This K is just complex conjugation. So in general, you can write T as a unitary transform operation UT times this complex conjugation. You can square T and do some math here and actually prove that then T squared must be either 1 or minus 1. Okay. So for bosons, you can actually, or if you have spinless particles, T squared is going to be 1. And for spin 1/2 particles is equal to minus 1. So actually for, for electrons, you will have just, or for spin 1/2, this form is the canonical form of the time reversal operator. So if you have, if you are going to the Bagaliu-Lejeune equation, because you are doubling the system, you have particle and holes, so your Bagaliu-Lejeune equation or Hamiltonian is 4×4, then you have to increase, so you have to apply this time reversal to the electron-like block and to the hole-like block, so you have to make the tensor product so that you get 4×4 matrix for this time reversal operator. So then we have actually 3 possibilities regarding this time reversal symmetry. One is that there is no time reversal symmetry. The other one, there is, and t is equal to 1, and there is, and t is equal to minus 1. So we have 3 possibilities from there. So I will stop, I think we are on time, so I will stop here, and then we will continue tomorrow this story. Okay?
Thank you.
You're welcome.
Questions?
Yeah, questions.
So t squared equals to minus 1 means you add this operator to maybe x. You will get a minus. Okay.
Seren?
I'm hard to imagine that this minus 1.
What? Which?
I mean, for the t squared is equals to minus 1, how does it? Like, what is physical? You actually act on the maybe.
Oh, you just square the. So you put this and act on this, you just will get minus 1. So we can do it if you want. So it's.
Yeah, I know.
It's just for,
I think what is confusing is that t changed t to minus t, and if you apply it second terms, it would be minus t to minus t, which is t. But
so
where internal degrees of freedom is minus identity. I think that's what probably.
So I'm not sure which, what was your discussion? Which line are you discussing?
That just means if you act t squared on the p.
On P? Yeah, but it depends which T is the one that you are using.
Correct?
It depends which is the well, for P, it's just gonna be like this. Yes. So you don't see why it changed P to minus P?
No, the t squared. If you apply on t, you will not get the minus. I think that's.
T squared on P?
Yeah.
Yeah, but it doesn't have to be minus P. Of course, if you apply this T twice to P, it's not going to change because it's, the first time you change it and the second time you change it back. So
Yeah, but if the c squared is equal to minus 1, then why? Why don't you won't get the minus?
Yeah, I think that's exactly David's question. That t square is minus 1 is true only on the spin degrees of freedom.
Right, yes.
Yeah, not
Not on the, yeah. So you see for this minus 1 is when you have a spin, okay? You have this sigma, this I sigma y here. So
the
you,
operator is like a P operator and identity matrix in the sigma spin, in the spin. But I think what Alex is telling that how the P is acting on spin or
Okay.
and then it's like a
Mhm.
yeah, but it's counterintuitive.
Okay.
Time reversal of fermions is kind of mystical, or not mystical, but yeah.
so actually, all these operators are actually, this for time reversal, it's tricky to find them because first it depends on the basis. So you change the basis, they will have different form, and sometimes you can actually combine them with some other symmetries and actually extend the classes. So that, you may have some symmetry class with, if you define this canonical, but if you combine this with other symmetries, you may find some sort of generalized version of these operators and extend this symmetry class. So to find what exactly you are going to use is sometimes tricky. Okay? All right, so we'll continue tomorrow.